In this video, we're going to be looking at compositions of functions and combinations of things that we can do with functions. So the first thing we have to talk about when dealing with functions is domain. Domain is a huge, huge thing we always have to consider when we're working with functions. So if a function f does not model data or verbal conditions, its domain is the largest set of real numbers for which the value of f of x is a real number. So we're saying, what are all of the possible things we could plug into the function and get something back out? So the main thing to consider with domain is really what to exclude. We go off the assumption that everything works, and we want to see then what doesn't work. So exclude from a function's domain real numbers that cause division by 0 and real numbers that result in an even root, such as a square root of a negative number. So those are the two main things we can't do in math. We can never divide by 0. We cannot take square roots or even roots of negative numbers. That leads to imaginaries. So those are the main two things that we're going to look for and use that to guide us. So if we're finding the domain of these functions, when I look at function a, x squared minus 7x, I'm not dividing by a variable. I've got no types of radicals, so that means everything is going to work. I can plug in whatever I want here. So my domain here would be all real numbers. If we put it in interval form, we'd say everything from negative infinity to positive infinity. Now for b, I see that I am dividing with a variable in the denominator. So I need to figure out when would this denominator be 0, because that's when we're going to have an issue. Now this is a quadratic. So I don't care about my numerator, right? It's just the denominator being 0 that's a problem. So I need to factor this. That's always our favorite way to solve quadratics. So I'm looking for two numbers that multiply to get to -3 and add to get to -2. Well, that would be -3 and +1. So just like we would do if we were solving, we set each of those factors, in this case, not equal to 0. And so we'd have our domain issues at +3 and at -1. Now, if we want to write this in interval form, this is where it gets a little weird, because we have to say, well, everybody else is included except those values. So we're going to start the way we always do with interval form, which is starting at negative infinity. But then we can go all the way up till our first issue, which is at -1. And this is where now I just say, well, I can't include -1, so it's going to have a parentheses. So that's part of what I have, but now I need to consider the rest of it. So I'm going to have a union because I've got multiple pieces here. Now I still want all the other numbers that are close to -1, just not -1. So I'm just going to use another parentheses again, starting now at -1. So that way I'm just saying I can get everything up to -1, and now we're talking about things after it, but the parentheses means we're not going to include the -1. So we trundle along -1 until we get to our next problem, which is at 3. And so then it's the same idea. I'm not going to include the 3, so we're going to use our parentheses. We're going to union it. Again, we're going to then start our next interval at 3. And we have no more problem areas, so we should be good all the way up until we get to positive infinity. So it's a little annoying in that notation, right? All right, let's look then at C. We've got a radical here. So no dividing this time, but I do have a radical. So I need to make sure the stuff under the radical has to be positive. So 3x plus 12 has to be greater than or equal to 0. I'm okay having 0 under a radical. All right, so from here, we can subtract the 12. And so we divide by 3. We know that we have to have values of x that are greater than or equal to -4. So in our interval notation, -4 then is our smallest value going up to positive infinity. But you'll notice in D, we actually have more things going on, because I actually have a situation with both of my problems. I'm dividing by a variable, and that variable actually ends up being in a radical. So I have to make sure the stuff under the radical is positive, but this time I cannot be equal to 0, because that would cause a dividing by 0 error. So I'm going to take the stuff under the radical, 14 minus 2x, and I say it has to be greater than 0. So we cannot include 0 since it's in the denominator. We subtract the 14. And when we divide by 2, we make sure that we flip that inequality. So we get that x is less than 7. So in our interval form, since we're less than 7, our smallest value is negative infinity, and 7 then is going to be our biggest value. So now we're going to work with multiple functions. Okay, so let's say we have f and g are two functions. We can deal with their sum, their difference, their product, and their quotient. So they're going to have domains for the set of all real numbers common to the domains of the two functions. And it is what you would expect it to be. If I say f plus g of x, I'm going to be adding my two functions together. F minus g of x, I'm subtracting my functions. Now, order matters with subtraction, so you have to be careful there. F times g means we're multiplying, and f divided by g means we're going to divide the functions. But we do have to make sure we're not having any domain issues because we're dividing by a function. Right? So let's say we've got these two functions, 2x minus 1, and then x squared plus x minus 2. So the first thing we're going to do is we're just going to add. So when we add, order doesn't matter. So I don't need any type of parentheses or anything here. I can just combine my like terms. So x squared is going to come first. We'll have 2x plus x, which is going to be 3x. And then negative 1 plus 2 is going to be, oh, that's a minus 2. Wonder why I didn't match my key. Negative 1 minus 2 is going to be a negative 3. Now we are supposed to determine the domain. So since this is a quadratic, no issues, domain would be all real numbers. Part B. So now we need to be careful because we're doing f minus g and subtraction order matters. So my first function, 2x minus 1, I'm good. But when I subtract, I'm subtracting the whole other function. So I need to make sure to use parentheses. So from here, we can distribute that negative. So we'll have 2x minus 1, a minus x squared, a minus x, and now we get a plus 2. So again, combining like terms, we'll have a negative x squared. 2x minus x is x, and negative 1 plus 2 is 1. Once again, when I'm thinking domain, I've got no issues here. So it's going to be all real numbers. Now C, we're going to multiply. So this is where we're going to have to use our distributive property. So usually what I like to do is I take my first term from the first set of parentheses and multiply it throughout. And then I'll take my second term and multiply it throughout. And then we can combine. So 2x times x squared becomes 2x cubed. 2x times x is 2x squared. And 2x times negative 2 is negative 4x. Then I multiply. Negative 1 times x squared is negative x squared. Negative 1 times x is negative x. And negative 1 times negative 2 is positive 2. Now we can combine our like terms. So let's see. We'll have 2x squared minus an x squared is 1x squared. Negative 4x minus x is going to be a negative 5x. And then plus 2. Again, no domain issues, so our domain should be all real numbers. And now we need to divide. So we're dividing function f divided by function g. So that'll be the 2x minus 1 divided by x squared plus x minus 2. Now, when we're dividing, we do want to see if this can simplify. So I'm going to factor in my denominator. So it is a quadratic, a nice one. We're looking for two numbers that multiply to get to negative 2 and add to get to a 1. So that should be positive 2 and negative 1. Now, my numerator doesn't factor at all, so this can't simplify any further. There is our quotient. So now we are going to have domain issues, though, because I have those two pieces, those two factors in the denominator. I know that both of those cannot be equal to 0. So that means x can't be negative 2 and x can't be positive 1 would be my domain for this guy. All right, so the next thing is composition of functions. So a composition of functions is when you have one function inside of another function. Now, it doesn't have to be anything complicated, right? You could have a function be x plus 2 and going inside something else. That's pretty simple, but it's the idea of putting one function inside of another function, and that's what our composition is. So our notation looks like this. So that open circle, we'd read that as compose. So this says f compose g of x. Now, I tend to prefer this notation over here. I think it's easier to see what's happening. So I'd read this notation as f of g of x. And so it's really easy then for me to see that g of x is going to be going inside of function f. So it's the inside piece. Okay, so we do have to think about domain here. We're going to check two places. So we have to be in the domain of G. So that's our inside function. So that's the first place you're going to check for domain issues is the inside function. And then you're actually going to do that composition. Ooh, sorry, we're going to do this later. I'm on the wrong part. That's all right. We'll get there. Domain. The main thing is our inside function is we're gonna check that one. We'll check something else later. We'll talk about it when we get there. So this is just going into this idea of putting one function inside of another function. G is inside of f of x. So when we do compositions, we're always working from the inside out when we're evaluating. So that's always the main thing I think about with compositions. All right, so we've got two functions here. We've got new functions f and g. We're going to do each of the following. So this says f compose g of x. So I always start by rewriting it into this notation because I like it better. So this would be, I'd rewrite it as f of g of x. So basically here what I'm saying is I'm going to replace my input into function f with what function g is. So this means I'm going to be plugging in x squared minus 2x plus 6 inside of function f. So that means anywhere where I saw an x in the original function, I'm going to replace it with that function of g. So what does this look like? Well, it's my function f says I take 3 times my input. So this is going to become 3 times my input. But that's the thing that's changing. G is now my input. And so that's where I'm going to put my x squared minus 2x plus 6. So that's 3 times my input, and then I still have the minus 4. So we can simplify this a little bit, right? We can distribute that negative. We'll get a minus 6x, plus 18, and then a minus 4. Combine like terms, and then plus 14. So this would be what we get when we compose f of g of x. So we'll do the same thing over here, but now doing our composition the other way. So this says g compose f of x. So I write that as g of f of x. So now what I'm doing is I'm putting function f inside of function g. So I'm using function f, which is this, and I'm going to put it inside as the input into function g. So what does this look like? So g of 3x minus 4. There we go. Okay, so function g says I'm going to take my input, which in this case is 3x minus 4, and I'm going to square that minus 2 times my input, which is 3x minus 4. And then to that, I'm going to add 6. So just anywhere I had an x in that function, I replace it with a 3x minus 4. All right, so what's our result? So 3x minus 4 squared. Using the rule for squaring a binomial, you start by squaring the first term. So 3x, that quantity squared, 3x times 3x, that becomes 9x squared. And then you're going to multiply, you're going to, in this case, subtract because we've got a minus in between, double the product of the terms. So 3x times 4 is going to be 12x. We double that to get 24x. And then plus the last term squared. So plus that negative 4 squared, which is going to be 16. We can distribute that negative 2. So negative 2 times 3x is negative 6x. And negative 2 times negative 4 is an 8. And then we'll still have the plus 6 on the outside. So combining like terms, negative 24 minus 6 is going to be minus 30x. 16 plus 8 is 24, plus another 6 is going to be 30. So the last part here is, now we're actually going to plug in a number. So this says g of f of 1. So you kind of have your option on how you can do that. You can find f of 1 first, and then plug that number into function g. But I already found g of f of x. So I really can just go ahead and use this function right here and plug it in to this. And then what do we get? So the negative 30 and the plus 30 are going to cancel out. So we should end up with an answer of just 9. All right, now let's talk about domain of the compositions. So now we're thinking of our excluded values. Okay, so excluded values from our domain would be X is not in the domain of G. Now notice G is the input. Okay, so we have to exclude values from the inside function. So the first place you're checking for domain issues is going to be your inside function, whatever is the one that's going inside. The second place you're going to check are things that are not in the domain of f composed g of x. So the composed function. So that means I don't really care about what's happening to the outside function, in this case function f, because I'm not using it in its normalness, right? I'm only using it after I plugged something else into it. So we just need to check the domain of the inside function and check the domain of the composed function. That's going to tell us where our issues would be. So if we've got this guy here, so we're doing f compose g of x. So that's f of g of x. That means I'm taking f of, and then I'm putting in function g. So function g is that 3 over x. Okay, so anywhere where I have an x in this function, I'm replacing it with that 3 over x. So function f says I take 2 over my input. So this is where I'm going to do that change. That becomes the 3 over x. And then we'll have the minus 1. So if we want to kind of simplify this, we've got a fraction in the denominator. So hopefully we recognize we've seen this type of thing before. We're going to need to actually subtract those to simplify, right? So what we're going to do is, well, I've only got one fraction. So when I do my common denominator, that's the only denominator. So my 3 over x is going to stay put. My constant, though, negative 1, it needs that common denominator. So I'm going to multiply it by the denominator that I have, which is x over x. So this is going to become 3. Negative 1 times x is going to be a negative x over x. So that's my denominator, right? So this is still 2 over, but my denominator now becomes 3 minus x over x. From here, we can use our idea of fractions over fractions, right? 2 in my numerator is the same thing as 2 over 1. So we can keep that numerator fraction the same, and we multiply by the reciprocal of the denominator. And when we multiply that together, we end up with 2x over 3 minus x. So that would be our composed function. And so then we need to check our domain issues. So remember, we're going to check 2 places for the domain. We're going to take the inside function. So that's our 3 over x. And we're going to take the composed function. That's where we're going to get our domain issues. So my inside function here is the 3 over x. So I just care about the x in the denominator. That tells me x cannot be equal to 0. And then I need to look at the composed function. So that's my 3 minus x. That can't be equal to 0, which means negative x can't be equal to negative 3, which means positive x can't be equal to positive 3. And so that's where we're going to have our domain issues. So the last thing to talk about is decomposing. So basically working backwards. So when you form a composite function, you compose 2 functions to form a new function. So it's also possible to reverse this process. That is, you can decompose a given function and express it as a composition. So although there is more than one way to do this, it's often more natural selection that comes to mind. So for example, they've got a function here where they've got this quantity raised to the 5th power. And so what this function does is it takes this inside piece, right, the parentheses, and it raises it to a power. So it makes sense that if we think about this as a composition, the thing that's inside is the stuff that's inside of the parentheses. So oftentimes when you're trying to decompose, you want to look for parentheses. So that is going to come from, things raised to a power. That could come from a radical. right? Because you can rewrite a radical as something raised to a power. When we get to trig, you could look to see what's happening inside of a trig function. You might have some composition inside of a trig function. So those are usually the places to look. So if we're, for example, here looking at this one, okay, so again, I'm looking for stuff in parentheses or stuff under a radical. Well, I can see that this is under a radical. So if I'm considering this as, you know, this composition of f of g of x, my inside piece, right, I can call that g of x. So here I would call my g of x the inside part, which is the x squared plus 1. So my function f is the stuff on the outside, right? So what is the outside part of this? Well, that's the radical part. So my function f of x, I could call that cube root of x.